Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Periodicity. So we need to start with a discussion of the structure of the periodic table, which you will have met in pre-A-level chemistry, I am sure. There are one or two features to bring out. Firstly, of course, the ordering of the elements 1, 2, 3, 4, 5, up to 10, then 11, 12. That is in atomic number and not in relative atomic mass. So it is the atomic or proton number which orders the elements. We then, at pre-A level, will have met the idea of groups. So if you remember the numbering, group 1, group 2, group 3, group 4, 5, 6, 7, and 0. And of course the groups we study at pre-A level chemistry, because if we take, say, group 1, then we know that they've got similar chemical properties. They all react with water in similar ways, but of course there is a trend in reactivity. Rubidium is considerably more reactive than lithium. But what we don't really discuss in pre-A level chemistry is the idea of periodicity. That is the trends in physical and chemical properties across the periods. So if we take period 3, sodium through to argon, then we will see, as we continue our studies of this, that physical properties change, melting points, boiling points, etc., densities, but that's also reflected in their chemical properties. Start with metals on the left-hand side, running through to non-metals, etc., on the right. So the study of the trends in the periods, left to right, so the periods are the horizontal rows. So the third period is sodium through to argon. The study of the trends in both physical and chemical properties is the subject of this topic. Let's consider the periodic trend in electron configuration. So I'd like you to pause the video and write the subshell configurations for the elements of the second period. Come back, check your answers when you have done that. Okay, so here are the correct configurations. I'll just remind you of the basics if you are not sure. The lowest energy subshell is 1s. The next energy subshell is 2s. So the capacity of 1s, as with all s subshells, is 2. So lithium has 3 electrons, 2 go into 1s, so 1s2, and the 1 remaining goes into 2s. Similarly for beryllium with 4 electrons, 1s2, 2s2. Boron with 5 electrons, 1s2, 2s2. The s subshells are now full, so we go to the next lowest energy subshell, which is P. The P subshell has a capacity for 6, so that continues to fill until we get to neon. I'd now like you to, for the third period, write the subshell configurations. Pause the video, complete that, and come back to check your answers. So here are the correct answers for the subshells or configurations for the third period. So Sodium 1s2, 2s2, 2p6, 3s1. So as a core, it has the neon electron configuration, 1s2, 2s2, 2p6. Then the additional 11th electron goes into the next lowest energy subshell, which is the 3s. Moving on, magnesium with 12 electrons ends with 3s2, and then we go to our 13th electron goes into the 3p subshell, which has capacity for 6, which explains argon being 1s2, 2s2, 2p6, 3s2, 3p6. Now, what can we learn from this? Well, we can see that group 1 elements, the highest energy electron is in an s subshell for both lithium and for sodium. For beryllium, we have the highest energy electron in an s subshell, and for magnesium, highest energy electron in an s subshell. So a new labeling of group 1 and group 2 is to be called S block. That is, their highest energy electrons are in the S subshell. Now if we move to boron, we see the highest energy electron is in a P subshell, similarly for aluminium, and then that is true for the remainder of the elements running from group 3 to group 0. The highest energy electrons are in a P subshell, so those are labelled P block elements. So just to map that onto a periodic table, groups 1 and 2, group 1 and group 2, they have their highest energy electrons in an S subshell, so they are S block. Groups 3 to 0, their highest energy electrons are in a P subshell, so they are known as P block. You will recall from having written subshell configurations for the transition metals that their highest energy electron is placed in a D subshell, so these are known as D block elements. So the S, D and P labeling within the periodic table is expected to be known. The S block elements, their highest energy electron is in an S subshell. D block element, the highest energy electron is in a D subshell. The P block element, the highest energy electron is in a P subshell. Electron configurations are linked to ionization energies. So we have periodic trends in electron configurations, and these are reflected in the periodic trends in ionization energies. So the first thing we need to clarify is what is meant by successive ionization energies. Well, here is an equation that expresses the first ionization energy of an atom M. Look carefully at that equation, pause the video and write a definition of the first ionization energy. Okay, so you can see here in the equation that we have 1 mole of gaseous atoms losing 1 mole of electrons, forming 1 mole of unipositive gaseous ions. So we need to include the mole quantity in our definition. So here is our definition of the first ionization energy. The energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. There's no variation on that. That has to be followed exactly. But that's the first ionization energy. What about the second? Can you write an equation for the second ionization energy? Pause the video, restart when you're ready. Okay, so here is the equation for the second ionization energy. Now, you may or may not have got this correct because a little bit of experience helps here. We don't start with the atom anymore, we start with the one positive ion that we formed in the first ionization. Then the second ionization starts with the 1 plus ion, forms the 2 plus ion by the loss of a mole of electrons. So 1 mole of gaseous 1 plus ions forming 1 mole of gaseous 2 plus ions. Can you write an expression for the third ionization energy? Okay, so hopefully you are in the groove. M2 plus loses 1 mole of electrons. So 1 mole of 2 plus ions, gaseous, loses 1 mole of electrons, and etc, etc. So ionization energies continue up to the numbers of electrons within an atom. So for sodium, atomic number 11, sodium has 11 ionization energies, the first, the second, the third, etc, up to the 11th, and so on for the other elements and however many electrons they have. So successive ionization energy values are supportive or are a main piece of evidence for the electron configurations in shells that you've been using since you started chemistry at pre-A level, GCSE. So let's look at an example for the successive ionization energy data for magnesium. So there we have here the number of ionizations, so first ionization, second, third, up to the 12. Magnesium has 12 electrons. Here is the ionization energy value, but you can see that it ranges from 738 kilojoules per mole to 189,371 kilojoules per mole. Now that is does not make for sensible graphing, so that's why chemists and physical scientists convert data of that range into logarithmic data. So I've taken the logs of those data, logs to the base 10, and I'm going to plot the log to the base 10 of the ionization energy against the successive ionization energy number. And here is the resulting graph. Now, you can see here that we have a group of 2 electrons that are relatively easy to remove. Then we have a group of 8 electrons that are not so easy to remove, and then we have 2 electrons that are very difficult to remove. So we reflect that as the 2 electrons closest to the nucleus, then 8 electrons at a distance or at a shell further from the nucleus, and then the outer shell contains 2. So that's where we get our electron configurations in shells from. Successive ionization energy data. 2 electrons are very easy to remove, they must be furthest from the nucleus. 8 electrons are not so easy to remove, they're in the middle. And then we have 2 electrons that are very difficult to remove, and they must be closest to the nucleus. So we have a shell or groups of electrons grouped by the energy needed to remove them of 2, 8, 2. So successive ionization energy data supports the electron configurations in shells that you have been writing. But we can do a little bit better than that, because given electron ionization energy data, we can look for the jumps. So we can see here that there's a big jump between the second and the third. Between the second and the third there's a big jump. Between the 10th and the 11th there's a big jump. So we know that there are 2 electrons that are easy to remove because there's a big jump to remove the third. And then we know that there's 2 electrons that are very difficult to remove because there's a jump between the 10th and the 11th. So rather than drawing graphs, we just interpret raw data. So we've got 2 electrons that are easy to remove, 8 electrons that are less easy to remove, and 2 electrons that are very difficult to remove. So what we're looking for is jumps in the data. We've gone from 1451 to nearly 8,000. That's a large jump. So that tells us that we've got 2 electrons that are easy to remove. That is 2 electrons in the outer shell. So try these 2 problems. The issue is, in which group of the periodic table is element X? So interpret the successive ionization energy data for element X, and then question 2, same idea, in which group of the periodic tables is element Z? So again, interpret the successive ionization energy data. Pause the video, produce your answers, come back to check whether they're correct or not. So here is the answer to number 1. It is group 4. The reason being that 1,000, 2,000, 4.5, 6, there's a big jump here. So having removed 4 electrons, there's a big jump to remove the 5th. So we've got 4 electrons in the outer shell, and then 2 more electrons inside. So we've got 4 electrons in the outer shell. That is group 4. So the second question, you might want to pause and try that if you didn't get the first one right, but otherwise I'm going to reveal the answer. This is group 7. Again, we're looking for a jump, and it's here between the 7th and the 8th. So there are 7 electrons that are easy to remove, and then there are some more electrons that are more difficult to remove. We don't know how many because it may be the 13th, 14th, 15th, but ionization energy. But we've got 7 that are relatively easy to remove, then a big jump to the 8th. So 7 in the outer shell. So that must be, as we know, group 7 has 7 electrons in the outer shell. So what is the trend in the first ionization energy down a group in the periodic table? Well, so our basic starting points are that the first electron lost in first ionization is from the outer shell, and that the reason that energy is required to remove an electron from the outer shell is that there's an attraction between the nucleus and that electron, or those electrons. Now there are 3 factors that affect the strength of the attraction between the electron and the nucleus, called nuclear attraction. Those 3 factors are atomic radius, something called shielding, and nuclear charge. So I'd like you to pause the video and write down how you think the size of the atom, the atomic radius, will affect the strength of the nuclear attraction. That is the attraction between the nucleus and the outer shell electron. So how will the size of the atom, the atomic radius, affect that? How will shielding, that is the presence of inner shells of electrons, affect that nuclear attraction? And how will the charge on the nucleus, the numbers of protons in the nucleus, affect that nuclear attraction? So one at a time, think it through, write down how you think those 3 factors, each in turn, will affect the attraction felt by the outer shell electron for the nucleus. Pause the video, come back when you are ready. Okay, so The atomic radius, well, the further the outer shell from the nucleus, then as we are thinking of the attraction being electrostatic, which is distance sensitive, then the further from the nucleus the outer shell, the weaker the nuclear attraction, and the more easily the electron removed. Shielding, electrons in inner shells, well, they have a repulsive effect by virtue of their negative charge. So they will repel outer shell electrons, and so that will have an effect of weakening nuclear attraction. And nuclear charge, well, the more protons in the nucleus, the stronger the nuclear attraction for the electrons, including the electrons in the outer shell. So we still need to conclude about the effect on first ionization energy of going down the group. So we've got two groups there, group 1, group 7. The trend in first ionization energy down the group is the same for both groups for the same reasons. The factors you need to consider are atomic radius, shielding, nuclear charge. I'd like you to pause the video and write out how you think going down the group will affect atomic radius and how a change in atomic radius will affect nuclear attraction. Could you do the same for shielding? As you go further down the group, what is the change in shielding and how does that affect nuclear attraction? And as you go further down the group, what is the change in nuclear charge and how will that affect nuclear attraction? Take your time, think your answers through, write them out and come back and check when you are ready. Okay, so as you go down the group, well, the atom gets bigger and the distance between the nucleus and the outer shell increases, so there is weaker nuclear attraction as you go down the group. As you go down the group, there are more inner shells of electrons, so that is going to increase electron-electron repulsions from within the atom, and so as you go down the group, the weaker the nuclear attraction. But as you go down the group, the nuclear charge will increase, which will make nuclear attraction stronger. So what we need to do now is to conclude overall what is the trend in first ionization energy down the group. Well, overall the effect is to weaken nuclear attraction. The weakening caused by atomic radius and shielding outweighs the strengthening caused by an increase in nuclear charge. Atomic radius is particularly influential. So the first ionization energies at the bottom of the group are lower, that is, it's much easier to remove an electron from rubidium than from lithium, from iodine than from fluorine. We can find evidence for subshells by plotting first ionization energy data against atomic number. So I've done this here, and I bring to your attention that at the three peaks we find noble gases. So noble gases within each period are the element that is hardest to ionize. That is, they have stable electron configurations. In the troughs we find group 1 elements. So they are easiest to ionize. That again would fit with our understanding of reactivity. However, what we need to explain is the general trend across period 2 that is repeated in period 3 of an increase going left to right. So as we go from group 1 to group 0, there's an increase in first ionization energy, and that is repeated in all the periods. Could you pause the video and, using the ideas of atomic radius, shielding and nuclear charge, come up with an explanation for that general trend? Pause and come back when you are ready. Okay, so going lithium to neon, lithium's got an atomic number of 3, neon an atomic number of 10. So we've got an increase in the numbers of protons and therefore in the nuclear charge. And that of course is true for sodium, which has 11, and argon 18 protons. So as we go left to right across the periods, there's an increase in nuclear charge due to an increase in numbers of protons. There's also an increase in electrons, so as we go left to right, there are also additional electrons, but they are placed in the same shell. So the distance from the nucleus remains approximately the same for each additional electron, and the inner shell's shielding remains the same. So two factors, the distance from the nucleus to the outer shell and the numbers of inner shells, remains the same. The only thing that changes significantly is the nuclear charge as we go left to right. Now, with an increase in nuclear charge, we see increase in nuclear attraction and an increase in ionization energy. So that is our explanation for this repeated trend going across each period. So having explained the general increase in ionization energy across each period, we need to look at the minor peaks that occur. For instance, there's a minor peak at beryllium and a minor trough at boron. That is repeated at the elements magnesium and aluminium. So we need to come up with an explanation of why beryllium is harder to ionize than boron, and then we get a repetition of that. Magnesium is harder to ionize than aluminium. Pause the video and, thinking in terms of subshells, come up with an explanation. Well, the explanation lies in the electron configurations of the two elements. If we compare beryllium and boron, we know that beryllium has got 4 electrons, and if we write that in subshells, it's 1s2, 2s2. If we write boron, which has got 5 electrons, 1s2, 2s2, 2p1. So we're looking to remove 1 electron from beryllium and 1 electron from boron. Well, the electron to remove in boron is in a higher energy subshell, so it will be easier to remove. So this peak here supports the idea that beryllium is more stable than boron. That is, boron's highest energy electron is in a p subshell, a higher energy subshell, and is therefore easier to remove. And we can look at magnesium. If we look at magnesium, it's 1s2, 2s2, 2p6, 3s2, whereas aluminium, 1s2, 2s2, 2p6, 3s2, and I'll just squeeze it down here, 3p1. Again, the highest energy electron in the aluminium configuration is in a higher energy subshell. So we are supporting, or this graphing, these minor peaks support the idea that beryllium is more stable than boron. The electron configuration of beryllium is more stable than that of boron, and that's repeated for magnesium compared to aluminium. And that supports the idea that the 5th electron in boron is placed in a higher energy subshell, 2p, and the 13th electron for aluminium is placed in a higher energy subshell, 3p, rather than in the same shell of the same energy that the other 2 electrons in the 3rd shell are. So the first 2 electrons from aluminium are placed in 3s2, but the 3rd electron in the 3rd shell is placed in a higher energy subshell, and therefore it is easier to remove. There is another minor peak that needs to be explained, and that peak occurs between nitrogen and oxygen, and then is repeated between phosphorus and sulfur. And again, we need to look at electron configurations to explain those minor peaks, but we also need to look at the configurations in terms of orbitals. So if we look at nitrogen, you know it's 1s2, 2s2, 2p3. So if I draw out the electrons in boxes notation for the 2p3, we see that the electrons will occupy an orbital singly. Oxygen, on the other hand, 1s2, 2s2, 2p4. Again, if I draw out the 3 boxes for the p subshell, we'll find that oxygen has to pair. Now, pairing produces increased electron-electron repulsions. So, if there's increased electron-electron repulsions here, that means the electron will be easier to remove, and we find that is the case. We have exactly the same situation for phosphorus versus sulfur. It's 3p3 for phosphorus and 3p4, the highest energy electron subshells for sulfur. So again, we have electron pairing for sulfur, orbitals occupied singly for phosphorus. So again, we see that sulfur is easier to ionize. It's easier to remove an electron because of the increased electron repulsions in the sulfur electron configuration. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.